So for this first question, we were given a conversion table with pressure units and asked to complete it using the value 275 millimeters of mercury. The top row of the table includes the pressure units, millimeters of mercury, kilopascals, torr, and atmospheres. The first value given in the bottom row is 275 millimeters of mercury, and we are asked to convert the amounts into the other units. To do this, we'll use the following standard conversion relationships. 1 atmosphere equals 760 millimeters of mercury. 1 atmosphere equals 101.325 kilopascals, and 1 millimeter of mercury equals 1 torr. So to convert millimeters of mercury to kilopascals, we'll do 275 over 760, which comes out to be 0.3618. And then we'll multiply that by 101.325, which comes out to be 36.67. So under kilopascals, it'll be 36.67. To convert millimeters of mercury to atmospheres, we divide the given millimeters of mercury value by 760. So we'll do 275 divided by 760, which comes out to be 0.3618 atmospheres. And since 1 millimeter of mercury is equal to 1 torr, we can just say 275 millimeters of mercury equals 275 torr. And this is the completed table. And so for this next question, if the volume of a gas decreases to 1/3 of its original volume while the temperature stays the same, then the pressure of the gas will increase. This relationship between the pressure and the volume is described by Boyle's law. And essentially, Boyle's law's formula is initial pressure and initial volume equals final pressure and final volume. So if the volume decreases to 1/3 of the original volume, that means the final volume equals 1/3 of the initial volume. So to solve for the final pressure, we have to plug in the formula. So it will be P1V1 equals P2, and in parentheses, 1/3 of volume 1. And now we need to divide both sides by 1/3 of the initial volume, which brings us to the final answer. If the volume of a gas decreases to 1/3 of its original volume while the temperature remains constant, the final pressure will be 3 times greater than the initial pressure. All right, so for this next question, we need to calculate the final pressure of a gas if the volume is decreased to 1/3 and temperature is doubled, assuming the number of moles remains the same. So for this question, we need to use the combined gas law, which is initial pressure and initial volume over initial temperature, and that equals final pressure and final volume over final temperature. So to solve for the final pressure, we need to multiply both sides by temperature, the final temperature over the final volume to isolate final pressure. And then after that, we can plug in the known values. So the volume decreases to 1/3. So final volume equals 1/3 of volume 1. And the temperature doubles. So the final temperature equals 2 times the initial temperature. So plugging that into the equation, we will get initial pressure, initial volume over initial temperature equals final pressure, and in parentheses, 1/3 of the initial volume over 2 times the initial temperature. And then we cancel out the initial volume and the initial temperature from both sides. And we multiply the denominator 3 times 2, which comes out to be 6. And we multiply both sides by 6, and that comes out to be the final pressure equals 6 times the pressure of the initial pressure. All right, and for this next question, an ideal gas sample occupies 1.50 liters at 25 degrees Celsius and 741 millimeters of mercury. How many moles are in that sample? So first we need to use the ideal gas law, which is pressure times volume equals number of moles times ideal gas constant times temperature. And moving on to the next step, we need to convert pressure from millimeters of mercury to atmospheres. So we'll do 741 over 760, which comes out to be 0.974 atmospheres. And we additionally need to convert temperature from Celsius to Kelvin, which is 25 plus 273.15, which comes out to be 298.15. Now we need to rearrange the ideal gas law equation to solve for number of moles. This will look like N equals P times V over R times T. And this equation essentially will be with our values 0.974 times 1.50 over 0.0821 times 298.15. And the final value will come out to be 0.0597 moles. And for this next question, what volume would the 0.25 moles of gas sample occupy at STP? Once again, we'll use the ideal gas law again. But once again, we're going to have to rearrange the values. So the new equation will be V equals N times R times T over P. And to plug in those values, we will have 0.25 times 0.0821 times 273.15 over 1. And that'll calculate out to be 5.611 liters. But for this answer, we need to round to three significant figures, so it'll be 5.61 liters of STP. And for this next question, we need to derive the given equations to calculate density of a gas. So we are given the ideal gas law, the density formula, and the mole formula. So we'll start with the ideal gas law, and we'll substitute number of moles equals moles over mass. So this will be PV equals M over M times RT. Now to solve for M over V, we divide both sides by V. And we know that M over V equals density, so the new equation will be P equals D times R times T over M. And to solve for density, we will rewrite the equation to be D equals P times M over R times T. And that is the final derived equation. And for the next equation, we use the equation that we just created for density of a gas to find what is the molar mass of this gas if its density at STP is 0.901 grams to liters. So we will plug in our values, and the equation will look like 0.901 times 0.0821 times 273.15 over 1, which will come out to be 20.22 on top and 1 on the bottom, and that will bring our final answer to 20.2. For this next equation, we're asked which component H2O2 or CO2 exerts the highest partial pressure in gaseous mixture made of 0.50 moles of H2 and 0.49 moles of O2 and 0.48 moles of CO2. So first we need to find the number of moles, and for H2 it's 0.50, for O2 it's 0.49 moles, and for CO2 it's 0.48 moles. And to total those moles, we add them together, and that'll come out to be 1.47 moles. And to find the mole fractions here, we divide the number of moles versus the total moles. So it'll be 0.50 over 1.47, which comes out to be 3.40. And for O2, it is 0.49 over 1.47, which comes out to be 0.333. And for CO2, the equation is 0.48 over 1.47, which comes out to be 0.327. So essentially, the hydrogen gas exerts the highest partial pressure with its value at 3.4 or 0.340. And for this next equation, we're asked which of the following mixtures exerts the highest total pressure in a 5.0 liter container. And usually we would use the ideal gas law for this equation, but since R, T, and V are the same for all mixtures, the mixture with the most total moles of gas will exert the highest pressure. So we do addition with all the values that we are given, and for A, it'll come out to be 1.5 moles. For B, it'll come out to be 1.4 moles, and for C, it'll come out to be 1.6 moles, giving us C having the highest total pressure. And for this next question, a 50.0 liter cylinder contains 2.00 grams of hydrogen gas and 12.0 grams of nitrogen gas at 25 degrees Celsius. And we need to calculate the mole fraction of each gas and calculate the partial pressure of each gas. So first we need to convert grams to moles. So for hydrogen, the molar mass equals 2.016. So we will do 2 grams over 2.016, which comes out to be 0.9921 moles. And for nitrogen, the molar mass is 28.02, so we will do 12.0 grams over 28.02 grams to moles, which comes out to be 0.4283 moles. And we add those together and we get 1.4204 moles. And to get the mole fraction of each gas, we need to create an equation to find that. So we will do 0.9921 over 1.4204 for hydrogen, which comes out to be 0.6986. And the fraction for nitrogen is 0.4283 over 1.4204 equals 0.3014. And to find the total pressure using the ideal gas law, we will plug in our values, and the equation will come out to be 1.4204 times 0.08206 times 298.15 over 50, which comes out to be 0.6959 atmospheres. And to find partial pressures, we will multiply the value that we had just calculated times the mole fraction value. So for hydrogen, it will be 0.6986 times 0.6959, which equals 0.4863 atmospheres. For nitrogen, it'll be 0.3014 times 0.6959, which comes out to be 0.2096 atmospheres.